Hello everyone, my name is Daniel and I'm a PhD student at the Technion Institute of Technology in Israel. Today, I will present the work our group has been developing entitled MRI-Contrast Enhancement of Copper Oxide Nanoparticles Following Focused Ultrasound-Mediated Blood-Brain Barrier Disruption. As you may know, the blood-brain barrier and the blood-tumor barrier are major impediments for effective therapy and monitoring of brain tumors. Copper oxide nanoparticles have unique properties of imaging and treatment that can be potentially leveraged for theranostic purposes. This is because these particles were shown to mediate anti-tumor effects by causing DNA damage and subsequent apoptosis-mediated cell death, as well as depicting MRI-Contrast enhancement capability. In this project, we have chosen to start focusing on the diagnostic aspect of these particles, and we have hypothesized that focused ultrasound-mediated blood-brain barrier disruption would induce greater penetration of intravenously injected copper oxide nanoparticles in the mice brain. The nanoparticles we have used have 7 nanometers in diameter, as shown in the cryotemp picture on the left. Moreover, we have previously shown in an in vitro setting that these particles can linearly improve the contrast-to-noise ratio of MRI scans as the concentration of copper oxide nanoparticles is increased. Here, we have used a focused ultrasound platform comprising of a 1 MHz therapeutic transducer coupled to a custom-made acoustic lens focusing beams at a 4 mm depth. Our system transmitted pulses of 50 milliseconds in length at a pulse repetition frequency of 1 Hz. The pressure at the focus was of 0.8 megapascal and the treatment duration was of 1 minute. Immediately at the start of the sonications, SonoView ultrasound contrast agent was administered as well as Evans Blue for gross pathology assessment. A 9.4 Tesla MRI scanner was used to acquire images prior to and following injection. Treatment protocol consisted of applying focused ultrasound for BBB disruption, followed by an acquisition of a pre-contrast MRI scan. Then, copper oxide at a concentration of 4 mg per kilogram of animal was intravenously injected and subsequent 3 MRI scans were performed. At the end of these scans, the 2 treated mice were euthanized for growth pathology analysis. Here, we see the T1-weighted MRI scans acquired prior to and following copper oxide injection. Following injection, the treated region marked in red depicted an enhanced visual contrast. This was correlated to the Evans Blue extravasation region shown in the bottom right figure. The second mouse depicted a similar trend showing improved visual contrast as a function of time following injection. This co-localized once again with the region of Evans Blue extravasation. For quantifying this effect, we calculated the contrast-to-noise ratio. This was done by subtracting the mean intensity of the background from the mean intensity of the treated region, and then dividing the obtained value by the mean intensity of the background once again. We normalize the obtained CNR value by the pre-injection CNR for comparison purposes. As we see, the CNR of the treated region linearly increased, reaching up to 20% increase approximately 35 minutes post-injection. Linear approximation of the data points demonstrated high coefficient of determination, as we see here for the 2 mice. To summarize, 7 nanometers copper oxide nanoparticles successfully penetrated the region of focused ultrasound-mediated BBB disruption. Contrast enhancement of around 15 to 20% was obtained at the treated region at 35 minutes. Future studies are still required to optimize injection dose and to investigate the potential anti-glioma effects of copper oxide nanoparticles following focused ultrasound-mediated blood-brain barrier disruption. We would like to acknowledge our collaborators and our funding sources. Thank you.